Hi everyone, and welcome to this video where we explain a very popular clustering algorithm known as k-means. This is a very simple to understand and easy to implement clustering algorithm which has applications in each and every field. So let's get into it. After watching this video, you will have an idea of what clustering is and how k-means is a very intuitive approach towards clustering. Then we'll get into the k-means algorithm using a rough illustration. After that, we will try and find the optimum value of the number of clusters, which is k, and how we might approach solving the problem of finding the optimum k. Then we will have a short discussion about the advantages and drawbacks of this k-means algorithm. And then finally, we will implement the k-means algorithm using a Python code. So let's get into it. Okay. Now, what is clustering? So, in rough words, clustering is basically grouping similar things together. Now, to make this a little bit more precise, you in machine learning you are given a feature vector, which is a column of many features present. But what clustering does, clustering is mainly used in unsupervised learning. So we are not given the labels of this data, and clustering is basically asks us to find the similarity between these two. Okay, wait. In clustering, what we basically ask the machine to do is, we say this is the data and can you please split this data into 3 or 4 or whatever the number of groups we want. This is an unsupervised this is an unsupervised type of machine learning problem where we are not given the labels of the data, and for a very intuitive approach towards this clustering can be k-means. So this will be more clear once I explain the algorithm of k-means. But so if given a feature vector like this, you might ask how can we find the similarity between any two data points? So let's assume it's in 2 dimension, and this is a data point and this is a data point. How do you find the similarity between these two? It is of course going to be the distance between them. So as we'll see later, the metric plays a very important role in k-means clustering. Let us now get into the algorithm with the help of an intuitive example. Let us consider a 2-dimensional data set with x and y axis, these being x and y being the features of the data set. Let us take a data set something like this. Here, as we can see, the optimum number of clusters this data set can be clustered into is 2. Here I am cheating a little bit because the data set is in 2 dimensions. So we can see what the optimum number of clusters the data set can be clustered into. But as we increase the number of dimensions, it becomes very difficult to select the optimum k value to cluster the dataset into. when that's the case, we use the higher dimensional dataset will be discussed later. Now let us see how the k-means algorithm actually works. So what the k-means does is, it takes like two random points in the dataset, say here or here. Now these points may or may not be the data points in the dataset. As in, we can choose the yellow point to be this as well, but it's our choice again. So let us take these two random points. Now what the k-means algorithm does is, it calculates the distance of these 2 points to each and every point in the dataset. So it calculates this distance, Now it assigns to it takes these 2 points as 2 labels, 2 clusters, depending on the value of k, and it assigns to each data point a particular value of the cluster label. So if this data set is closer to this yellow point rather than the other one, then this data point is assigned to this label. Similarly for this label. So we can say that the approximate decision boundary is something like this. This is a straight line because we are taking the Euclidean distance. We could take some other distance and the decision boundary would be slanted, would not be a straight line, basically. Now what it does is, it assigns different labels to the different classes which we made earlier. So let us take the data below this decision boundary to be blue. And the above one, let us keep it as it is. So now what it does is, it takes the centroid of these 2 clusters individually. Say this cluster and this cluster. So it takes the centroid. Let us take the centroid to be somewhere here. This is the new, and now what it does is, it takes the new yellow point to be the centroid of these 2 clusters. So now, as you can guess, it again finds the distance of all these. Now, as you can guess, it again finds the distance between these points to the centroid of the cluster, and these points to this centroid of the cluster. Now it finds. Now what it does is, it repeats what we did in step 1 again. Repeat repeat the assignment from step 1. So basically it calculates the distance of all the points to these two yellow points, and then it again clusters it differently. So we can say, so let's say this point, my diagram is not perfect, but let us say this point is closer to this point, this yellow point, rather than this yellow point. So now this blue point, the point which was blue before, it now gets assigned to be red, this way. So similarly, this point is closer to this yellow point rather than this yellow point. So now this point gets a blue color. Similarly for this point as well. So it is pretty clear that as we increase the number of iterations, more and more points go to the clusters which it was supposed to go, as we can see from just looking at the data. So in the end, the data looks something like this. So all these points are blue and all the above points will be red. The decision boundary will be something like this. That is for the algorithm part. In our algorithm, the k value is a hyperparameter. Now, as mentioned before, by looking at the dataset, if the dataset is in 2 dimensions, by looking at the dataset, we can approximate the number of clusters as in the k value. But this task becomes extremely difficult as the number of dimensions increase. So how do you find the optimum k value for the dimensions more than 3 dimensions, let's say? This can be done using a method called elbow method. This method uses the basic fact that as you cluster the dataset into more and more clusters, the variance of each cluster decreases. Now let's say you have a dataset like this, something like this, let's say. So for k is equal to 1, it clusters all the data set into a single point. For k is equal to 2, it might consider two data points like this. Now when compared to k is equal to 1, the average variance between these two clusters is less compared to the total variance when we took the whole dataset as a cluster. This variance will become 0 when the value of k will be equal to the number of data points in the feature space. So we plot a graph between the k value and the average variance. of the dataset in each cluster. This plot looks something like this. It decreases steeply, then it saturates to a particular value. Now what this method says is that the optimum k value for any given clustering problem is the one at this particular point. This is called the elbow of the graph. Yeah, this method is actually very useful, but there have been other methods which have been developed after this. They say that this method is a bit ambiguous because the elbow point might as well be this point or this point, so it's a bit ambiguous. So they developed a method called the silhouette method. We won't go into the details of this method, but basically we get a graph which looks something like this, where here in the y-axis it's the silhouette score, and x-axis it's the k. Using this graph we can easily find out the optimum value of k, which is this. There'll be a unique value of k. Let us now get into the advantages and drawbacks of this method, of this k-means method. The advantage is, of course, it is very fast to implement for a large scale data, and it also guarantees convergence. It might be a bad convergence, but it surely converges. It is also very simple to understand and very intuitive as well. It also scales to large data sets. So it doesn't matter, the dimension of the data set is irrelevant, because you can always find the Euclidean distance between the points, even though it might be computationally expensive. Yeah, now let's get into the disadvantages of this method. One of the main disadvantages of this method is that it cannot classify outliers. As in, even if there is a single outlier, it ruins our whole clustering algorithm. So say you have a data set which is something like this. Now say you have an outlier somewhere around here. This outlier highly influences this cluster which happens here. So the median might be shifted here somewhere. Let's mark the centroid as red. The centroid will be shifted towards this point. So some of the points here, which were supposed to be marked as near to this point, this centroid, the centroid which belongs to this cluster, will be closer to the centroid which belongs to the other cluster. So some points might be misclassified. So this is the main drawback of this model. Some other drawbacks include the fact that we have to choose our K manually. Well, K needs to be manually updated. This is a problem with every hyperparameter in every machine learning model. And another important drawback is that it depends largely on the initial values. It depends up to a great extent. There's a whole field known as initial value. To find the initial values of this problem, it is initial values. Various different methods to find the initialization of these algorithms have been theorized, but we won't go into the detail of those methods as it is out of the scope of this video. Yeah. Okay, now let's get into the code which was implemented. I will open the Jupyter notebook and it will be explained.
Now I'll show how to implement k-means clustering in Python. First, I'll show how it's done using sklearn's k-means. This is a simple implementation. You can directly import k-means and then it's just 2-3 lines of code, and then I'll show you how it's done from scratch. Let's start by importing the dataset. For this, we'll be using sklearn's iris dataset. So let's from sklearn.datasets import load iris, and then we'll also scale this dataset from 0 to 1. Code min max scalar, and we'll also be plotting a lot, so let's also import matplotlib's pyplot as plt. Now the data will be in a dictionary format when you load iris, so we'll use the key data, and this will give us an array with four columns, and from there we're only interested in the middle two columns. And we'll also have to scale this data from 0 to 1. As I said, this can be very sensitive to scaling, so we are scaling this data from 0 to 1, which is equal to 0, 1, and we'll fit this to our training data. So this is it. Now to visualize the data, we'll plot it using pyplot. We'll do a scatter plot with black color, and this is our dataset. So you can see the clusters here clearly, and now we'll see how k-means is implemented through sklearn. So first we need to import sklearn. From sklearn.cluster we need to import k-means, and we need to create a k-means object with n cluster is equal to centers. Now we haven't defined what centers is, and right now after we write this line of code, and we need to fit this to data, and so let's say our centers is 3 and number of clusters is centers, right? And then we'll use cluster plotter, and we'll pass our data and our k-means dot labels. So k-means dot labels will return a label for each data point in data, a unique label. But as of right now, we do not have anything which plots this. So I've already written a plotter. I'll just copy paste the code for a plotter. So this is a plotter here. As you can see, what this does is it takes a dataset and labels, and then there is this dictionary which assigns each label a particular color. and then the data set gets, each point in the data set gets a particular color, and then it's plotted. So with this you can see the clustering with 3 centers, right? So these are the 3 clusters we have right now. So that's all there is to it. So implementation of k-means from sklearn is as simple as this. Okay, you want to implement this with 4 clusters, this is it. So these are the 4 clusters, and this is with 2 clusters. As you can see, k-means does not detect outliers, and this has been given the green cluster. It could have been very well a pointer belonging to the blue cluster, but there's nothing k-means does to detect outliers. Now we'll see how we can implement this from scratch, almost scratch. So first, we'll write this code for a single iteration where we create the centers, cluster the data, and then make the new centroids, and then we'll pass all of these into we'll create a recursive function from all of this, and then the recursive function will do the job and give us the final clusters. So let's just write one particular iteration. Say k is equal to 4, and I'm just defining a global k right now. This helps in something with the plotting you'll see later. So these are our centers here, and right now we'll only work with 2D data. For n-dimensional data, you can replace this with n, but we'll work with 2D data. So you can see the centers are 0 here. So these 4 points are the 4 centers we have. But this is not a good guess, of course. So what we'll do is Partition Initialization, which means we take samples from our datasets, from the dataset itself as initial centers. And there's another way to do it. It's called Partition Initialization. So wherein you create a partition of the dataset, and then you take the centroids of each partition as the centers. But we'll just go ahead with the Partition Initialization. So for Partition Initialization, for each centroid, which is the number of centroids is k, we write center I, 0, which is the x value, and this is the y value. This should be equal to a random data point, right? This is data point np.random length, or anything from 0 to the length of the dataset. And now you can see our centers will have random points, will be random points in the dataset. And okay, there's an error here. Should be I. Right. Now we'd like to visualize the clusters, and again I have a handy function here which I wrote. I'll just paste this function. What this function does is it takes data, the dataset, and plots it as black, and it takes the centers and plots the centers as red. And it can also take in the previous values, the previous centers, and it can through this code here, it can draw arrows from the previous centers to the new center. And with center plotter, as you can see, these red points are the centers and the black points are the data points. And now let's create the labels list. And in the labels list, for each point we'll have a corresponding label. The label will be the label corresponding to its nearest center. So the way to do it is we'll calculate the distance of each point from each of the centers, and then we'll check which is the nearest center, and then we'll assign a label corresponding to the nearest center. So I'll just copy paste the code here. So this is the code. This is the distances array, and as you can see, it has four in our case, general k values, and then we take the minimum value as the index of the minimum value, and we assign it as the label. So what's happening here is that say the index for each center is considered to be the label itself. So if you see the labels, these go from 0 to 3. And now we'll now our data set has been clustered, and we can see it using our cluster plotter. We'll pass data and labels. Right, so these are the four clusters we have: the green, the red, the cyan, and the blue. As you can see, this is a terrible clustering. I mean, everything is terrible since we have 4 Ks. This whole thing could have been one particular cluster, and these whole cluster could have been 3 particular clusters. Now we'll update each of the centers. So what we're doing here is, say this is one particular cluster, we'll calculate its centroid. This is another cluster, we'll calculate its centroid. This is the third cluster, we'll calculate its centroid, and this is the fourth cluster, we'll calculate its centroid. And our next centers will be these clusters, these centroids. So again, I'll paste the code here just to save some time. And what's happening here is, for each point, we're creating an array. For each label, say red, we're creating an array called filter, and then we're iterating through the whole data set through all these black points and storing each point with a red label. If label is equal to I, then we append this data point to filter, and this access is nice. And then here we calculate the centroids, and our new centers are the means of these filters. The means of these filters. So once we have done this, we can see how our centers have updated through center plotter, pass data set, and data and centers. As you can see, one of the centers have come down here. In the first run, all of the centers were here, the big cluster, in one of the clusters. But now, after one run, one of the centers have come down here. The centroid from here came down to here. That's about it. So this is the whole code. You start with some centers, you cluster the data, and then you update the centers as the means of the new cluster, the centroids of the new cluster. Now we'll use all of this code to create a recursive function, and the recursive function is created by just copy pasting all of the individual codes into one big function, and we'll keep a track of count, and if count exceeds 100, we'll raise an error saying maximum number of iterations has been reached. Besides this, this whole thing is the same as before. In the first count, we'll initialize centers, and then from then on, we'll use the new centers as centers. And if at any time the new centers are equal to the old centers, we'll return the labels. So that's where we end our clustering. In this part of the code, I've also used center first as false, so previous centers are passed, and so we can see arrows here. Let's see how our code works. So labels is equal to means clustering data comma 4, and cluster data comma. Right, so these are the 4 clusters we have, and here you can see the evolution of the centers. So initially our centers were here, then this centroid came here, you can see a small arrow, and then these have been moving ever so slightly, and they stabilized around here, and we get the clusters. We can now see how it's doing the clustering for two runs, 2 clusters. So these are the 2 clusters. Try to run it again. Okay. Now let's check. Just for fun, let's try another data set with 3 clusters. We'll use make blobs from sklearn.datasets to create a data set with 3 clusters instead of 2, and we'll run our own implementation of k-means on this data set. So dataset comma labels is equal to make blobs 100 points with 2 coordinates and 3 centers. And let's just check first how our dataset looks. Dataset. The x value. This is the y value, and we want to plot it in scatter plot of black color. So this has roughly three clusters. Let's try to run it again and see. Right. So this is a better dataset. We can clearly see 3 clusters here. And now let's try to implement let's try to see how our own implementation does 3 clusters. Labels is equal to k means clustering dataset comma 3 and cluster plotter dataset comma labels. So as you can see, our own implementation is doing very well. It has separated all these 3 clusters. If you want, we can just run this whole thing again with say 4 centers, and these are the 4 clusters. Let's see if our dataset can recognize this 4. As you can see, our implementation of k-means is doing very well, and that's it. Thank you for your time. Hope you learned something from our lecture.